Hi, my name is Jonathan Byrd, and this is the Egg Drop Project for Intro to Engineering, EGR 150 100A at Durham Technical Community College, taught by Professor Flavio Albuquerque. What is the Egg Drop Project? Design a contraption to catch a raw egg from a 6-foot drop. Use only polypropylene straws, less than 50 of them, and masking tape. The straws cannot be significantly altered, meaning you can't cut them into strips and then weave them together into a basket, that kind of thing. The masking tape can only join straws together. The device must work at least 5 consecutive times and be maintainable. So in my final design, there was a 60-gram egg mass. That'll be important in a minute. A 6-foot drop height. We already said that. So I used about 245 centimeters of masking tape, 48 polypropylene straws. The weight was 48 grams. And the time it took me was about 12 hours, which felt like a long time. But I've never done something like this before, and I learned a lot. While I'm building this second design here, I wanted to show you the hexagonal structure of the bottom. And my idea originally was that I wanted these, you see it only has 3 points of connection with this bottom support strut, and then 3 corners are not supported by that. There's no bar in here. What happens is each one of these corners that is not supported, let's pick this one right here, goes up this strut to the top of the basket, and that supports one of the struts that is the main support for the basket. So what happens when the force of the egg hits that basket and it pulls down, which I want it to do, I want it to displace by about 5 centimeters, which is enough room to sort of provide some stopping force to the egg without an unsustainable force and breaking that egg. When that pulls down, that can pull inward on this corner, and that can pull upward on this corner, which is not supported by this right here. So that distributes the elastic deformation among these different components so that I don't get destructive plastic deformation and still get plenty of room for this basket to displace. So there was some math behind this design. I didn't just go into it blindly. And the thing that I started with was the formula for kinetic energy, which is kinetic energy equals 1/2 the mass times velocity squared. So we have the mass, we can plug that in. It's 0.06 kilograms. Those are the units you would use for this formula. So 60 grams is 0.06 kilograms. So what we have to do is find the velocity. Well, we know we're dropping the egg from about 6 feet above the device. And the formula for getting the velocity of a falling object in free fall in Earth's gravitational field is the square root of 2 times the gravitational constant times the height in meters. So everything is in SI units here. So I'm going to plug the gravitational constant in, 9.81 meters per second squared. And 6 feet is about 2 meters. There's a slight difference, but it's close enough to get this estimate. So we get 6.26 meters per second, and I can plug that into the velocity in the former equation. So now we have everything, and it turns out to be about 1.18 joules of work that the egg is doing, the energy that the egg is bringing to the structure when it lands from having fallen for 2 meters. So I know that work equals force times displacement. And we're only dealing with a single direction here, so we don't have to do a dot product if you know what that is. And I did some looking around the internet, and I found that about 25 newtons is the maximum amount of force that an eggshell can resist. That's about where they start to break. So it was a little bit less than that, but I wanted to give it a margin for error. So, and then I know that the work is 1.18 joules. So the work times equals the force times displacement. So I can just rearrange that so that I divide the work by the force to get the displacement, which turns out to be 0.047 meters or about 4.7 centimeters. So that's how much I want the basket to descend when the egg hits it. That's how much space it's going to take for that basket to displace and stop the egg without providing so much stopping force that the egg breaks. So all of this relies on deformation. We're going to use deformation to absorb the energy of the egg. There's two different kinds of deformation. There's elastic deformation, where the material returns to its original state, which is great for resilient load-bearing components. You don't want those to change very much. You want them to come back to their original position. And then there's plastic deformation. So the material is irreversibly altered. This is great for non-load-bearing force absorption. So say like a highway cone or something that's made to stop or at least slow down a car that's going to hit it before it gets to the concrete barrier, which is not going to deform as much. You want to hit that barrel before you hit the concrete barrier. So that's plastic deformation. That barrel is going to have some give. In fact, an entire car now is made to crumple and absorb the force instead of your body absorbing it. So part of the design goal is also repeatability, as we said. So allowing elastic deformation maintains the integrity of the structure. So this is the first test. And I didn't start at 3 feet. I was just very confident, and I started at 6 feet. So let's watch here. Now we see, and we'll do it again one more time, and then I want to back it up. Okay, so let's look at this first one. When it hits the structure, this is the first time an egg ever hit the structure, and watch what happens to the back leg on the right side. Bam, you see it buckle out there in front of the door. You can just see it buckle out. And then the whole structure kind of twists, and you can also see in the front panel how the 3 straws sticking up on the left-hand side there, that's supposed to be a solid strut across there, but watch how it buckles outward. So we have some more plastic deformation there, and you see how the whole thing curves and kind of bounces, but the egg doesn't bounce very much. The structure has done a great job of absorbing the force. So the second time we see it kind of a similar thing. This time the strut on the right in the front buckles, and then that panel again sort of buckles outward. But it's a good showcase of how the egg can land not exactly in the center. It can land in various places around the side, and the structure still kind of works. However, I didn't like all that plastic deformation there on the sides and in the legs, so I did some reinforcement. So this is the second test from 6 feet again. And I just doubled up those struts on the side there. So you see we don't get that same buckling of the legs that we got. We get a little more bounce, but the legs don't buckle. They still come in, and most of the plastic deformation happens in the top of that basket. All right? I have 6 struts coming down from the 6 corners into the basket. Okay, but these 2 kind of come together to a point, and then these 2 come together to a point, and then these 2 come together to a point, and they all meet in this sort of triangle of straws that I put down here. And what this does is it puts a little twist on the basket, so when the egg hits the basket, it actually provides a little bit of a twisting force to this thing instead of it all being downward force. And what I found was that kept the unit from bouncing so much when it reacts to the force. You know, the basket goes down and it pops back up, and that sort of makes it bounce. But that twisting motion makes it twist a little bit more instead of bouncing so much. Here is the new version, and I actually had to cut some of these off. They were too close to the ground. I felt like they would stop the egg too soon and maybe break it with the force of that stop, especially on a hard surface. So the inside ended up being a little different. I sort of made it a little more asymmetrical to maybe increase that sort of curve that it did when the egg hit it with force, and the whole inside sort of curved a little bit, and the downward energy went into that spin instead, and it kept it from bouncing as well. So I like this new addition. The reinforced struts seem really nice. We're going to take it out and test it right now. All right, so this is the test of the new design. That's from 3 feet. So I did start from 3 feet with this one. That admirable. Yep, 3 feet. That's good. Seemed a little stiff. Let's see, that's from 6 feet. Oh, no. Let's see what happened there. it hits the basket, and the basket just doesn't move very much. So the egg didn't break in the basket, but the basket bounced the egg out, so that's not okay. I went and got another egg and tried it again, and the egg comes down and it hits the basket and it bounces out again. And I think the basket might be too strong, so I went and got the old contraption and put it in here and did more tests. Here, watch this. Perfect. I'll do it again from 6 feet. Bounced, but the thing bounced with it and caught it. Right? Let's see that again. Boom. It bounced almost down to the ground. It actually touches the ground there. The straws touch the ground. That's what I really wanted, was that displacement to give enough room for the basket to slow down to absorb the shock of the egg hitting it. It bounces, but again, the contraption bounces with it, and the egg is safe. So the plot twist is that this brand new thing that I made that's nice and strong and reinforced in all the places I wanted to reinforce it in, it breaks eggs. It's too strong. This thing that's like got plastic deformation here, and these things kind of have given way, and I had to reinforce the struts. But it doesn't break eggs. It's, it's soft enough, I guess. It got beat up a little bit, and it was soft in the beginning and had some plastic deformation. And I thought that wasn't good, but it's still going. I've dropped, 8 or 9, 10 eggs, a dozen maybe, and it's still going. So that's really what I learned from this whole project, is that plastic deformation was not as undesirable as I thought. There was some that I corrected for, even in the struts of that model. But having some of it there and having that softness and that floppiness actually helped it, because it doesn't bounce the egg out. The other one didn't break the egg in the basket, but it just bounced it right back out on the floor. And I'd already come very close to the maximum amount of straws that I could use for the project, so I couldn't sort of like make a cage around it to hold it in. And again, I'm out of time. So again, we have one of these issues where you got a project, you don't have enough time to minimize your resources or to do another redesign, but you have something that works. And it takes into account the safety and the project specifications. It meets the specifications. That's it. Whether you like it or not, whether you're proud of the work or not, you have a deadline, you've got to get it done. And that's what I did. So I hope you enjoyed this. I hope you like my egg drop catcher contraption. It's, like I said, it's beat up. It's like an old junkyard car, but it works. It's soft like an old couch, and it doesn't break an egg. So the final design used, again, about 245 centimeters of masking tape that I estimated 45 straws, and it weighed 45 grams. It's interesting, about a gram of straw for each design. So it was ugly. I'm not super proud of it, but it was successful. The first prototype was very successful, and that's the one that I kept. I met the deadline, and most importantly, I learned a lot from doing this project and from really putting the time in. These are my references. I didn't really reference a lot of things. I referenced one of my own physics textbooks, and this was my best reference for the forces, the Newton forces that an egg can sustain, from the National Science Foundation. Thanks so much to Professor Albuquerque, and thanks to you for watching. I hope you enjoyed it.